effects of 4 different starting stances on sprint time in collegiate volleyball players. Human Performance Laboratory, Department of Kinesiology, California State University, Fullerton, California. Introduction. The ability to accelerate over short distances is of paramount importance to success in many sports and as the focus of many training investigations when moving from point one to another in the least amount of time. Quickness is often the deciding factor. In volleyball, the few seconds or milliseconds of time taken to move to a ball may be the factor that determines winning and losing. Because the volleyball court is small in area, there is no time to reach maximal running speed. Therefore, quickness needs to be maximized. Volleyball players often start from an athletic position with their feet shoulder width apart and their knees bent with weight on the balls of their feet. From this position, they move forward to reach the ball or sprint. It may be beneficial to take a step backwards, often called a false step, FS, before moving forward. Stepping back involves an eccentric muscle action that can invoke the stretch-shortening cycle, SSC. The SSC subsequently increases concentric muscular force during push-off and may enhance performance. Hennessy and Kilty examined the relationship between the SSC and sprinting across different distances in well-trained women athletes and found significant correlations demonstrating that the SSC plays a vital role in sprint time. Similarly, Broad et al. Investigated vertical jump performance and found that an FS before jumping increased jump height. To propel the body forward maximally from a relatively stationary position, the center of mass must be situated in front of the support area. Recent research has indicated that an FS before acceleration creates a greater impulse, more horizontal power, and results in an increased displacement compared to no FS. The previous research has identified 2 important aspects: maximizing acceleration when sprinting, forward position of the body center of mass, and use of the SSC. However, little research has examined the effects of these on acceleration in volleyball players or use of a combination of stance involving both. Therefore, the purpose of this study was to examine the effect of 4 different starting stances on forward sprint time in collegiate volleyball players. Methods. Experimental approach to the problem. This study used a repeated measure designed by having male and female athletes compete a 15-foot sprint from a standing start using 4 different starting stances that manipulated the SSC, forward, body lean, or both. In this manner, we were able to evaluate the components of each stance individually and collectively to discern the mechanism underlying speed differences by stance. Subjects: 26 National Association of Intercollegiate Athletes, collegiate volleyball players, men, 13, age 20.85, plus or minus 2.79 years, height 191.28 plus or minus 8.51 centimeters, mass 83.52 plus or minus 11.77 kilograms, women, 13, age 19.31 plus or minus 1.25 years, 176.16 plus or minus 7.7 centimeters, mass 69.43 plus or minus 9.7 kilograms. Volunteered to participate in this study during their immediate off-season active rest period. The men's team won the national championship that year before, whereas the women's team won the national championship 2 years before. Testing was approved by the University Institutional Review Board, and all subjects read and signed an informed consent document before data collection. Procedures. Subjects were measured for height and weight using the standard health-o-meter scale, Jarden Corp, New York, USA. All tests were performed on a wooden volleyball court in 1 day, and each individual session lasted approximately 15 minutes. Subjects wore their normal volleyball shoes. For all tests, warm-up was considered of jogging around the volleyball court 3 times. They were then instructed on the 4 different starting stances. Stance 1 was parallel. Feet started even with toes behind the line, then began by stepping forward with the preferred foot, figure 1. Stance 2 was FS. Feet started in a parallel stance with toes behind the line, and then began by stepping back with a preferred step before stepping forward with their front foot. Figure 2. Stance 3 was staggered. Feet started with preferred foot forward and toes behind the line, then began by stepping forward with the back foot. Figure 3. Stance 4 was staggered fall step. SFS. Feet started in a staggered stance with preferred foot forward and toes behind the line, then began by switching feet before stepping forward with the front foot. Figure 4. During testing, the lead investigator stood at the end of the sprint lane and held a volleyball in an outstretched arm. Upon release the ball, subjects were instructed to sprint as fast as possible. The timing device was 15 feet long with an infrared sensor, model E3Z, Omron Electronics, Schaumburg, Illinois, USA, at each end attached to wooden boxes, 60 centimeters high. To record stop and stop of each sprint trial, the start line was 30 centimeters behind their first pair of sensors to prevent extraneous movement from prematurely breaking the beams. A cone was placed 5 foot beyond the second pair of sensors as a finish line. Figure 5. Breaking the lights sent a signal to a laptop computer using a data pack 2K2 acquisition software, Run Technologies, Mission Viejo, California, USA, which sampled at 1000 Hertz and measured time between signals in milliseconds. Each stance was performed in random order for 3 trials with 30-second rest between trials and 1 minute rest between stances. This resulted in a work-rest ratio of approximately 1:30, giving adequate rest. Statistical analysis. All statistical analysis were performed via PASW 18.0 statistical software, SPSS Incorporated, Chicago, Illinois, USA, and the significance was set at a priority of 0.05 reliability for each stance was way analysis of variance, ANOVA. Each stance was addressed with the interclass correlation coefficient. One-way analysis of variance, ANOVA, was used to analyze age, height, and weight by sex. Before sprint time analysis, sphericity was checked and was not violated, and order effects were checked and none were found. A 4x2 stance by sex mixed factor ANOVA analysis sprint time for interactions and main effects. Significant main effects were followed up with simple ANOVAs to determine pairways differences. Average time of the 3 trials for each stance was used for data analysis. Results. Men were taller and heavier than women, but their age was not different. Interclass correlation coefficient values for each stance ranged between 0.63 and 0.83. There was no significant interclass of stance by sex. There were main effects for both sex and stance. The main effect for sex demonstrated that men were faster than women. Follow-up pairways comparisons of the main effect for stance demonstrated that the FS 1.18 plus or minus 0.10 seconds, staggered 1.16 plus or minus 0.07 seconds, and staggered FS 1.14 plus or minus 0.06 seconds stances were all faster than the parallel stance, 1.25 plus or minus 0.09 seconds. Also, the staggered FS stance, 1.14 plus or minus 0.06 seconds, was faster than the FS stance, 1.18 plus or minus 0.10 seconds, figure 6. Discussion. The results of this study demonstrated that men were faster than women and that stances involved a staggered were all faster than the parallel stance. The use of an FS to accelerate forward has been regarded as an inferior starting style because intuitively it seems counterproductive to an athlete's performance. This study indicates that starting with a staggered stance, whether employing an FS or not, produces the faster forward sprint time over an initial 15-foot in collegiate men and women volleyball players. Research done in previous studies has examined only 3 different starting stances, parallel, FS, and staggered, whereas our study added a 4th, the SFS, because it commonly used by volleyball players. In this stance, the athletes started in a staggered position with the preferred foot forward and had to switch their feet before sprinting. The decrease in sprint time with this stance may have been because of a combination of them being able to activate the SSC and produce a forward position of their center of mass. our study tested volleyball athletes running at maximum acceleration for 15 feet, 3 meters, whereas other studies have tested volleyball athletes for 5 or 10 meters. We draw this distance to make it as volleyball specific as possible because with 6 players per side, each volleyball player rarely runs over 15 feet to reach a ball. Direct observations. To measure 30 feet, around 10 meters would be of little value because the court is only 60 feet in length, and therefore 30 feet of each play in half. We also tested a special population, collegiate volleyball players, whereas other studies have used recreationally trained subjects. Lastly, we included the use of the staggered FS stance designed to activate the SSC and increase forward body lean. Although taking an FS or beginning with staggered feet seems counterproductive, the resultant SSC likely increases force production off the push-off phase, therefore decreasing sprint time. When an athlete steps back, there is an eccentric muscle action via lengthening of the calf muscle, which activates muscle spindles, causing a signal to be sent to the spinal cord, which in turn sends a reflex back to the muscle, serving to increase force production during the subsequent concentric muscle action. A stagger stance might produce greater speeds by reducing movement time because the feet are already in a position of taking an FS from a parallel stance. With a parallel stance, the center of mass must be repositioned in front of the feet before the horizontal force can be developed. This delay, in combination with the absence of an SSC action, may not be conducive to increasing acceleration over short distances, thus resulting in slower sprint times. Subjects in our study ran slower using the parallel stance when compared to all other stances. Similarly, in previous studies, the parallel stance was found to be significantly slower than the FS for both 5 and 10 meter differences, whereas another study found FS sprint times to be significantly faster when compared to a parallel stance at 2.5 and 5 meters. Karen et al. Quantified the position combination to push off from a backward step of the leg before acceleration. Subjects performed a sprint start using 3 different stances, starting just in front of the force plate and then stepping back, or starting on the force plate with no backward step, and starting with one leg in front of the force plate and the push-off leg on the force plate. The push-off force was greater when beginning in front of the force plate and stepping back, which also had the shortest time to build up push-off force. This increased force should lead to greater speed and lower sprint times. Regarding force production in the forward direction, Karen et al. Found that the parallel starting was significantly slower than FS sprint times. This may be so because the athlete did not step back. To initiate forward movement from a stationary starting position, the center of mass must be positioned anteriorly to the base of support feet. This is achieved in one of 2 ways: a rotation of the body about the ankle joint, thereby shifting the center of mass forward, or by displacing the area behind the center of mass, placing 1 foot backward. Also, a start step with a step backwards requires a shorter time to build up push-off force and increase peak push-off force, this increasing acceleration. Harold and Steele examined the biomechanics of a sprint start and found that once a sprinter has left the blocks at a low angle, 40 to 45 degrees relative to the ground, the next 2 steps should occur with the total body center of mass ahead of the contracting foot at foot strike to minimize braking force. In other words, the first 2 steps need to be behind the center of mass to increase forward lean during acceleration. Positioning the center of mass ahead of the contacting foot for the first 2 steps encourages increased horizontal force production. This is not achieved in the parallel stance, but is maximized in the staggered stance. Conan et al. Investigated the effects of parallel split and FS on 5 and 10 meter sprint times and found a parallel stance to be significantly slower than the other 2 stances at both distances. This is likely because the parallel starting stance does not invoke the SSC to produce optimum force production, or the center of mass starts behind the base of support. Their results suggest that there may not be any advantage to using a forward step as would be done in a parallel stance. In conclusion, our study only examined a sprinting movement in the forward direction only for a distance of 15 feet. Therefore, our results may not be applicable to diagonal or side-to-side movements of the SSC, and forward center of mass may not be maximized in these motions because of different body positions. Additionally, our study excluded any effective reaction time on sprint speed, which may have added additional milliseconds to the total sprint time in a stance-specific manner. Future research should explore the different starting stances on diagonal and side-to-side movements while investigating total sprint time, including that required for reaction to a stimulus. Practical applications. Volleyball players should use either an SFS or a staggered stance before accelerating in a forward direction to decrease sprint time over an initial 15-foot distance. Because the goal of any quick movement is to move from one point to another as fast as possible, employing either of these stances appears to decrease sprint time, thereby increasing sprint and probability of reaching the ball. Coaches should also conduct training sessions for these specific movements to maximize their athletes' familiarity and subsequent game performance.